Hi everyone, welcome back to the channel. In today's video, part 3 of our TinyUSB series, we are going to understand how the FAT file system works and implement a pseudo FAT12 file system. In the next video, we will integrate our file system with Raspberry Pi Pico using the TinyUSB. So what will be our objective? Understand the FAT file system and the various building blocks of it like boot sector, understanding FATs, understanding the FAT root directory, understanding FAT's data storage. And finally, we will be bringing it all together by implementing a pseudo FAT12 file system. Let's start with the basic. FAT, or file allocation table, was first developed by Microsoft back in late 1970. Originally, it was developed for floppy disk. The increase in disk drive capacity over time drove modification to design that resulted in versions FAT12, 16, 32, and exFAT. FAT was replaced by NTFS as the default file system on Microsoft operating system with Windows XP. Today it is used in USB devices, SD card, multimedia cards, and eMMC because of its compatibility across OS and embedded system. The boot sector is the very first sector of a FAT volume. On the right you can see all the various properties present in the boot sector. The boot record occupies one sector, usually the 512 bytes. It always placed in the logical sector number 0 of the partition. It contains the executable bootstrap code and essential file data. It includes BPP or BIOS parameter block, which hold critical details such as number of FATs, sectors per clusters, and so on. It also includes extended BP block, which adds more details such as volume ID, volume label, file system type, etc. This area helps identifying the file system type FAT12, 16, or 32 and provides pointer needed by the OS to locate and manage file allocation tables and data cluster. The boot record blends bootloader code and file system metadata, critical for system startup and management in the FAT. Next up, the file allocation table. It's essentially a giant array that acts like a linked list for the file cluster. Each entry points to the next cluster in the file. There can be more than one FAT depending on the BPP. It's located right after the boot sector. The size of each FAT entry changes depending on the file system version. Precisely what the 12, 16, 32 number indicates, the size of the FAT entry in the bits. Each entry contains number of the next cluster in the file or a marker for end of the file, unused disk space, bed or reserve space. Check out this example. Let's trace file A. The directory tells us that file A starts at cluster 2, so we look at second entry in the FAT. The value there is 0x003, which means the next part of the file cluster is cluster 3. So we jump to entry 3, which points to cluster 4, and so on. This continues until we hit a spatial end of file or EOF marker. It's a beautiful, simple way to handle file data fragmented all over the disk. Now we come to the root directory. So how do we find the starting cluster? That's the job of the root directory. The metadata of a file directory is represented as a root directory entry data structure. It contains a list of directory entries, basically of 32 bytes each. It contains file or directory names and sizes, file attributes, creation and modification dates, and the most important part, the starting cluster number. This is the number that gives us entry point into the file allocation table. The name field follows 8+3 file name scheme. The first 8 bytes for the file name padded with spaces. The last 3 bytes are for the file extensions. Finally, we have the data area. This is where all the file and directory contents are actually stored. This area starts at cluster 2 since cluster 0 and 1 are reserved. The key rule here is each cluster can only hold data from a single file. So to recap, the OS reads the boot sector to understand the disk layout. It then looks into the root directory to find the file's name and its starting cluster. Then it uses the starting cluster to navigate the file allocation table, jumping from cluster to cluster until it hits the end of the file, reading the actual data from the data area along the way. Simple but effective. Alright, enough theory. Let's see some code. We are going to build a simple FAT12 file system. Here I have defined two constants for our virtual disk. The disk max num sector means our disk will have 16 sectors in total. This sector size means each sector is 512 bytes, which is the standard sector size in most storage disks, including hard drive, SD card, and FAT formatted volumes. For simplicity, we will have 5012 bytes per sector, 1 sector per cluster, 1 FAT table, 1 sector per boot, FAT and root directory, no hidden and last sectors, 2 files in our TinyUSB MC, volume, file 1 and file 2. Each file will only consume 1 sector, that is 1 cluster. Total root directory entry will be 16. Total sectors in our volume will be 16. I have created another enum called sector index. This gives meaningful name to specific sectors in our disk. So instead of saying sector 0, I can just say boot sector. Finally, the last line creates the disk in the memory. It's just a 2-dimensional array of bytes or 8 KB of virtual disk. Initially, I am setting everything to 0, meaning that the disk is blank, no data, no files yet. Later in the code, we will fill these sectors with the boot sector info, FAT table directories and file content. First, we will initialize the boot sector. Before we can fill into the boot sector, let's first understand what the boot sector structure looks like in FAT12. I have defined a C structure called the FAT boot sector, and each field directly maps to what actually stored in the first 512 bytes of a formatted disk. This structure is a direct representation of boot sector layout on the disk. The attribute packed flag ensures the compiler doesn't insert any padding bytes because it's a real disk. Every byte has a specific position. The structure is divided into 3 main parts. The jump code plus OEM name. These are the very start of the sector, the first 11 bytes. The jump code is an instruction for bootable disk and OEM name is labeled as MS-DOS 5.0. Next is BIOS parameter block. This sector describes the geometry of the disk, how many bytes per sector, number of FATs, root directory entries and total sector. Basically, it tells the OS how to interpret the rest of the disk. And last, we have extended boot record. Added in later FAT version, this stores metadata like drive number, volume label, system ID, FAT12 or 16 and ends with a mandatory signature 05AA. Now let's point to the start of our virtual disk first sector. That's where we will store this structure. Here we copy the jump instruction and OEM string into the specific field. Next we fill the actual FAT parameters, how big the disk is, how many FAT tables it has, how many root directory entries are allowed and so on. Here 0FAT defines that it's a fixed hard drive. Finally we fill the extended boot record. This includes the drive number, serial number, volume ID, system ID and final signature 0xAA5. We give the drive number 0x80 for indicating that this is the first hard disk and the boot signature 0x29 to tell the system that this is in a modern FAT format. Once this structure is written to our first sector, our disk officially looks like a valid FAT12 volume. Next, we will put some content in our files. This is the easy part. We just mem copy a string into the sector we have designated for file 1 and file 2. Again, the hex dump just shows how our text displays directly to the disk image. Now the next region of FAT12 volume is the root directory. This is the area that holds an array of directory entries, each 32 bytes long, describing files, folder or even the volume label. Think of it like a table of contents for the disk. Each directory follows a strict 32 byte format. It contains the file name, file attributes, creation and modification timestamp, and the cluster number where the file data actually starts. The very first entry in the root directory is usually a volume ID entry. This is not a file or a folder. It's a label identifying the disk itself. Here the attribute volume ID marks this entry as the volume label. It doesn't have a starting cluster or a file size. Those fields are 0. The timestamp are just demonstration values. Now that the volume ID is set, we can move to the next entry in the record directory. This represents the actual files on the disk. Each file gets its own 32 byte directory where we have specified the file name, attribute, timestamp, starting cluster and file size. Here we are defining first file file_1.txt. The attribute archive marks it as a regular data file. The timestamp are encoded using the macro FAT time and FAT date. The important part here is that the first cluster low, which means the file starts at cluster 2, the first available data cluster after the reserved one. Finally, file size is set to the length of the string we copied earlier into the data sector. Then we continue to the next entry for the next file. The next entry defines our second file, file underscore .txt. This file starts at cluster 3, which maps to the next data sector. Notice how each file cluster member matches the data region we initialized earlier. In FAT table, entries 0 and 1 are reserved. In the hex output, you can clearly see the ASCII names of the files followed by the attribute byte, timestamp fields, cluster numbers, and finally the file size at the end of each entry. Now that we have defined the boot sector, root directory, and the file data, the last key piece of FAT file system is the FAT table itself, the file allocation table. This is where the file system keeps the track of which clusters are free, used, or linked together for a file. In the FAT12, each entry is 12 bits, not a full 16 or 32. That means each cluster's entry overlaps with the next one slightly. It takes 1.5 byte per cluster entry. The first 3 bytes represent the two reserved FAT entries, cluster 0 and 1. Cluster 0 contains the media descriptor byte 0xFAT for a hard drive or a fixed disk. Together with the next byte, this marks cluster 0 and 1 are reserved and unavailable for data. Next, we mark cluster 2 and 3, our two files, as 0FFF, which means end of the file. This tells the FAT system that 3 cluster contains a complete file and do not link to any other clusters. For demonstration, what I did was I created a file called FAT12.c, and from the main function I'm calling a function fs underscore init. In the fs init, we are creating the whole FAT12 file system in a global array MSC disk. So here you can see we are initializing the boot sector. Then we dump our files into their respective location. Then we created the root directory for the volume ID, then for the file 1, then for the file 2. Then at the last we created the FAT table for both of our file entries. After this, what we are doing is we are opening a file called fat12 underscore fs.img, and we are dumping the whole structure onto that file. This is so that we can mount this image in our Linux system to see the file contents. So let me compile it. I have a typo here, disk block size.
A few moments later.
Now let's try to compile it again. Now it got compiled. Now let's run the program. We see that a file got created. Let's see the content of the file using the file command. You can see the boot sector has been read and we got the following information. We see that OEM, we got the OEM name, number of FAT, count 1, root directory entries is 16, sector 16, media descriptor F8, sectors per FAT is 1, sector per track is 0, head, and this is our volume ID tinyusb.msc. Great. We can also get the detailed information using the fstate program about our file. So this is file system type FAT12, OEM name, volume ID. We can see the boot sector, root directory name, boot sector, volume label, file type entry, sector before file system 0, total range 0 to 15, that what we have. Reserved 0, boot sector 0, FAT is at 1, data area is from 2 to 15, root directory is 2, cluster area starts from 3 to 15. So metadata is this, root directory there are 2, sector size 15, cluster size 512, total cluster range 2 to 14. And FAT file contains, there is only one cluster for a file, so you can see 3 to 3 is EOF and 4 to 4 is EOF. So this is reflecting correct to our implementation because our file is constrained in only one sector or one cluster. Great. Next step, what we'll do is we'll try to mount this file system to a temporary folder in our Linux system so that we can validate if our files are present there or not. So first let's make a temporary directory. Then let's mount our directory as a loop to this location. Let's ls. Great, it got mounted. Now let's ls to this location. We can see two files. Let's see the size of the file. 31 bytes, 31 bytes. It's aligning to what we have added. If we can see, this is I think 31 byte only, or 32. Let's cat file1, file1, cat. This is the first file. The content of the first file seems so correct. Seems correct. And the next. So we can see the file contains in our file system is correctly represented after mounting it. We have successfully created a FAT12 file system from scratch and our OS can read it perfectly. Now let's be a good citizen and unmount our file system. You mount. Yeah, it is unmounted. And that concludes the demo. Alright, that brings us to the end of the video. In this session, we learned about the FAT file system and understood its memory layout. How different sectors like boot sector, FAT table, root directory, and data area fit together. We then implemented our own FAT12 file system from scratch step by step. After that, we validated our implementation using tools like file and fstat to confirm the correct file system structure. Finally, we mounted our FAT12 image on a Linux machine and verified that the files we created were actually accessible, proving our implementation works. In the next video, we will take it a step further by integrating our FAT12 file system with Raspberry Pi Pico using TinyUSB. Like always, the source code for the entire project is available on my GitHub repo. You can find the link in the description below. If you found this video helpful, don't forget to like, share and subscribe so you don't miss the next video. Thank you for watching and see you in the next one.